So I actually want to start by going over a little better what I was explaining at the end last time. So Alice sends an n-dimensional state. That is a state of, she sends a quantum system with an n-dimensional Hilbert space. To Bob. And the aim is to show that Bob can extract at most log n, actually log 2n, bits of data from this. And we know a simple strategy that can achieve that because there's no need to use quantum mechanics. Bob and Alice are allowed to have a prearranged code here. So Alice could simply have a set of n orthogonal states, sends one of them to Bob, Bob measures it, extracts one out of n possible outcomes, and therefore log 2n of data. The goal of the discussion was to try to explain that no quantum strategy does better. So let's discuss in general what a quantum strategy would be. So first of all, Alice creates, well, there's some message n she's trying to send. So her notebook has the projection operator into state n, and then she sends an nth density matrix of some system B to Bob. So Bob receives system B, and is supposed to extract meaning from it. Well, extracting meaning means you make some kind of measurements, possibly after some other manipulations. So let's discuss what a measurement is. Measurement means there's a device, M, the measuring device, which is arranged so that its final density matrix is diagonal in some known basis. So quantum mechanics books in a clear way get as far as explaining that the measuring device is diagonal, has a diagonal density matrix in a known basis. And then in some undefined mysterious sense, you're supposed to know the value of M. Neither Bohr nor Everett nor anybody else explained what that step means. That's where quantum mechanics is really mysterious, in my opinion. But regardless, what that means is that the outcome, when all is said and done, when Bob has done whatever he's going to do to extract meaning, what matters is Alice's notebook and Bob's measuring device, and they both have diagonal density matrices in known bases. So we called Alice's basis n, and we called Bob's basis m. And there's some probability distribution, R of n and m. So the final state is simply a classical correlation between the measuring device and the original Alice's notebook. So now we have a purely classical question. Knowing the outcome of his measurement, how much does Bob actually learn about Alice's notebook? Well, we discussed that when we were on Zoom a few weeks ago. And the answer is that the mutual information between I and M is the number of bits Bob learns. Now this is per trial over many trials. You'll remember when we discussed classical information theory, it always involved very long messages or very repeated experiments and so on in order to get certain answers. But the classical mutual information between the measuring device and Alice's notebook measures how much Bob actually learned as a result of whatever he did. Now, knowing this, let's go back to what Bob does when he receives this signal. Well, okay. First of all, the density matrix before Bob manipulates it is a classical quantum density matrix that we discussed also in a previous lecture. This thing, which I'll call rho AB. And one thing we learned is that in that density matrix, the mutual information between A and B was this thing which is positive by convexity. I left out the fact that Alice has probabilities, P of n, for her message she's trying to send to be n. So it's the entropy of the average density matrix minus the average of the entropies. And since this last term is negative, this is equal to or less than the first term, which is log n. So our goal is to prove that the final meaning Bob extracts the meaning Bob extracts is equal to or less than log n. And that will follow So what we want to prove will follow if we show that the mutual information between Alice's notebook and Bob's measuring device is no more than the mutual information in this state before Bob does anything. Now, to deduce that, I went over that way too quickly on the blackboard probably. So the first step is that Bob has some, well, he has got equipment, let's say, C, and a measuring device, M. So the measuring device and the equipment start in some state rho Cm. So the whole system, Bob simply brings into contact B with Cm, but the initial state of just introducing Cm into the picture will do nothing to the mutual information. Okay. Then we want to say that the mutual information between A and BCM in the state rho ABCM is equal to what we simply called IAB in the state rho AB. That's intuitively obvious because there's no correlation between Cm and the rest of the system. So adding in Cm is not going to affect the mutual information if mutual information deserves its name. I'll let you check from the definitions that this step is correct. Then Bob applies a unit. So step one, maybe I should call step one, is to replace rho AB by rho AB Cm, defined this way. And that does nothing to the mutual information between the combined system Bob controls, which is BCM and A, simply because Cm is not correlated with anything else in the discussion. Step two is that Bob applies a unitary to the system under his control, which is BCM. That also doesn't change the mutual information. And step three is just to forget B and C and focus on the measuring device M. Because when we call M the measuring device, that means that whatever meaning Bob will extract, he will extract from the value shown by the measuring device. Now, this can only reduce the mutual information. So in other words, I of A relative to BCM, before forgetting B and C, is equal to or bigger than I of A and M. Now, that last statement is the deep one. It's equivalent to strong subadditivity. let me just use the abbreviation X for BC. So we're trying to say that I of A, xm, is equal to or bigger than I of A and M. If we write it out, that's just saying that SA plus SXM minus SAXM is equal to or bigger than SA plus SM minus SAM. And SA cancels. So we find that the inequality we need is SAM plus SXM is equal to or bigger than SM plus SAXM. And this is called strong subadditivity. And as we've discussed previously, it follows from monotonicity of relative entropy. So monotonicity of relative entropy is a deep statement, deeper than anything I've said about information theory, which we will say something about, I hope, next week. But I haven't given any explanation yet of why it's true, except that we proved it classically by a simple manipulation with logarithms. So if you put all the pieces together, we've established what we promised at the beginning, that by sending an n-dimensional quantum system to Bob, Alice cannot convey more than log n bits of information. But in order to prove that, we had to use this rather deep property of monotonicity of relative entropy, or because of what I've just told you, it's also, the fact we just used, this, is called monotonicity of mutual information. Classically, it tells you that if you know X and M, what that tells you about A is at least as much as you learn about A if you know about M only. To justify that interpretation quantum mechanically, that was not straightforward. The sort of thing I've told you, well, you could consider it rather limited, but we did show, in a certain sense, that the quantum mutual information bounds how much meaning you can extract from something. So, in my opinion, the kind of result I explained is typical of why the name quantum mutual information makes sense. So, for example, in a previous lecture, one of you asked me whether quantum mutual information refers to the information you extract in a single trial or many trials. I declined to answer at that time. And the reason I did was that I had not told you anything that justified the name quantum mutual information. So in order to answer the question, we need to know why quantum mutual information does have something to do with information. And this story I'm telling you is the first time I've told you anything that justifies that at all. Now, in the context of this story, you can see that the quantum mutual information tells you about information over many trials because we learned something about it by an inequality relating to classical information, mutual information. And we know that classical mutual information refers to information content in many trials. So that's as much as I'm going to say about this process, but we can stop for questions. Yes?
So I'm not sure I understand what one of the equipment is claimed. Why do we distinguish that from the measuring device?
Well, there might have been no equipment.
Okay.
But in general, there might be. So I don't know what Bob did in his lab. Alice sent an atom, let's say a spin 7/2 atom with an 8-dimensional quantum Hilbert space. Bob had a measuring device. I don't know what he did. Maybe he, to be general, we allow for the possibility that Bob has something other than the measuring device that played a role in his manipulation. If you want to assume that C was trivial, that was fine. I would have said exactly the same thing if we had assumed C was trivial, but then it would have been less general. I was trying to cover the most general thing Bob might do. Any other questions? No more questions? I'm going to tell you a slightly simpler version of this then. which maybe is the example I should have given to begin with, because explaining the story about Alice sending a quantum message to Bob turned out to be more complicated to explain on the blackboard than I realized. Here's a more symmetrical problem. So there's a quantum system that I'll call AB. It has a density matrix rho AB. Now, A is in Alice's lab. B is in Bob's lab. Now, in order for there to be an interesting correlation between systems A and B, at one time they were in physical contact, maybe in somebody else's lab. Somebody else created an interesting quantum state where A and B are correlated, entangled in some quantum fashion. And then A was sent to Alice, B was sent to Bob without disturbing that. Now Alice measures A, and Bob measures B. Well, the question is, how many bits of information can Alice extract about Bob's measurement and vice versa? In other words, Alice makes her measurements. She will know something about what Bob measured. Okay. The state rho AB is known to Alice and Bob. Otherwise, you can learn nothing about the other person's measurement. So for example, you might know that you have two spin half particles coupled to spin 0. So then if Alice measures spin up along the z-axis, she'll know that Bob definitely will get spin down along the z-axis. And then if Bob's measurement was to the spin along the z-axis, the answer will be 1 bit of information. But in general, for any measurement processed by Alice and any measurement processed by Bob, there will be some amount that Alice can predict about Bob's measurement and vice versa. And the question is, how much is that? Well, Alice and Bob will both have measuring devices. Let's call N Alice's measuring device, and M will be Bob's device. So measuring devices, as I've said, by definition, have diagonal density matrices. So at the end, there will be some density matrix for the combined system of the two measuring devices. It'll be a joint probability distribution for the values of N and M measured by Alice and Bob. And the answer to how much Alice learns about Bob's measurement and vice versa is just the mutual information between N and M in the state with density matrix rho N M. So to give an upper bound on how much Alice can predict about Bob's measurement and vice versa, we want an upper bound for rho N M. For I of N M. Now I claim that I of N and M in the final state is equal to or less than I of A and B in the initial state. The basis for this claim is essentially the same as it was in the previous explanation. What Alice will do will be to combine A with some measuring device and maybe some equipment, although she could leave out the equipment if she doesn't need it. Then she applies a unitary and forgets A and C. For Alice, I guess I called it N. Mapping to N. And by the same logic as before, so Alice will transform A into N, and then monotonicity of relative entropy says that will only reduce the relative mutual information. And then Bob similarly transforms B into M. And that, again, only reduces. So, at each step, each manipulation by either Alice or Bob never increases the mutual information, it can only reduce it. The possible steps, remember, are to bring up an uncorrelated system to add it to the discussion, that does nothing, to apply a unitary transformation, that does nothing, and a partial trace over some things you plan to not worry about anymore. That can reduce the mutual information. So regardless of what measurement strategy Alice and Bob take, and in general they could use generalized measurements, which we discussed on Tuesday, the amount of meaning, or the amount that Alice will learn about Bob's measurements or vice versa, has an upper bound, which is given by the mutual information of the initial state. So again, the reason I've explained these examples in part is to explain, well, at least to give you some idea that quantum mutual information deserves its name, but also in part to help you understand that monotonicity of relative entropy is important in being able to show that things like quantum mutual information do deserve their name. Now, any questions? Okay. Now, if there aren't any questions, then we're actually finished with what we're going to do on general quantum information theory. And we're going to head back toward quantum field theory. I'll explain some things that are in my article, Notes on Entanglement Properties. We previously discussed the Riesz-Leiter theorem, which was as much as I will say about section 2 of what's in those notes. And now I'm going to be telling you some things that are in sections 3 and 4, I guess. So we'll start by, okay, now I have a more specific goal though. I want to explain, so remember there's an we discussed the following situation. In quantum field theory, you divide space into two regions, A and B. Then, formally, you try to define a density matrix for observations in system A, but we find it's ultraviolet divergent. We did a special calculation in two-dimensional conformal field theory in one of the Zoom lectures where we computed this ultraviolet divergence. And we're going to study the same ultraviolet divergence today in a different way. But, so one goal is to see the ultraviolet divergence again. Now the second goal, so I made the assertion, I think, in the Zoom lecture, that the ultraviolet divergence means that the Hilbert space of the combined system can't be factored as a tensor product of two Hilbert spaces. But I want to explain better that infinite entanglement means that a region, A or B, has an algebra, not a Hilbert space. So that's the second goal. And then the third goal is going to be saying, well, what do we do instead? If a region doesn't have a density matrix, can we nevertheless extract some of the content that we had in ordinary quantum mechanics where a system can be assumed to have a density matrix? So these three things are what I aim to do in the next little bit, which I guess we'll go through Tuesday. After that, we'll do a few applications, which will be things like the Bekenstein bound, the C theorem, and the average null energy condition in Minkowski space. And then we'll go to black hole thermodynamics and the generalized second law. So those are the topics I'm hoping to cover in the rest of the course. But for step one, we're actually going to relate the UV divergence in the specific case of a CFT, of a conformal field theory, to an IR divergence. So let's remember one of the basic cases of a basic example of a density matrix. A thermal one. So a thermal density matrix at inverse temperature T. Is e to the minus beta h divided by a constant that's chosen so that the trace of rho is 1. The constant is called the partition function, of course. Well, we can compute this by Euclidean path integrals. Suppose we want the matrix element of rho beta, I'll call it, between an initial state psi and a final state psi tilde. Well, we could represent that by a Euclidean path integral with imaginary time beta and initial and final state psi and psi tilde at the two ends of the interval. Now, remember one thing we said about density matrices was that every density matrix can be purified. So remember that if rho is a density matrix on a Hilbert space H, there's always a pure state psi HH prime, let's say, in H tensor H prime, such that rho is the density matrix of the pure state psi. The trace over H prime of the projector onto psi H prime is equal to rho H. So that's something we learned right at the beginning when we discussed density matrices the first time. However, for the case of a thermal density matrix, there's a particularly nice realization, which is called the thermofield double. So the new Hilbert space is a second copy of H. Actually, more canonically, it's the time reversal conjugate. People usually refer to H tilde as a second copy, but if you're more careful, you'd call it the time reversal conjugate. And then the density the state, what I'll call the thermofield double state of the combined system, psi TFD. So we let I be the energy eigenstates of the original system, and I prime or maybe I tilde are the energy eigenstates of system H tilde. The thermofield double state is a sum over energy eigenstates of system I times energy eigenstates of system energy eigenstates of system H times energy eigenstates of system H tilde with a weight factor which is 1 over the square root of z. And the exponent is half as big. So from this definition, you can see that if you took the pure state density matrix, that would be 1 over z times the sum over I and j, e to the minus beta times ei plus ej over 2. Then you'd have ij for system H tensored with I tilde j tilde for system H tilde. Taking the partial trace would tell you to set I tilde equal to j tilde. So the trace over H tilde of this to take the partial trace, you would set the unobserved states of the second system with Hilbert space H tilde equal. So you'd set I tilde equals j tilde, which means I equals j. And then here, ei plus ej would just become, divided by 2 would just become ei. And that partial trace would be a thermal density matrix for the original system. The reason I said that H tilde is really the time reversal conjugate of H rather than being H is the following. In general, the states I don't have a natural phase. So this formula was a little bit ill-defined as written, as it's usually written. If H tilde is the time reversal conjugate of H, that means that if you change the phase of the state I, you would change the phase of the state I tilde by the opposite amount. So making system H tilde the time reversal conjugate of system H causes this expression to be well defined. A special case of that is that if system H is time reversal invariant, then you can simply say that H tilde and H are the same. Then you'd say that you fix the state of the phase of state I by saying it's invariant under time reversal. That actually fixes its phase up to a minus sign. But then, in the time reversal invariant case, you could say that H tilde and H are identical, so whatever sign you pick here, you pick here. And again, the expression is well defined. But in general, H tilde is really a time reversal conjugate. Now, we did this computation with formulas, but we could have done it more efficiently with path integrals. How do we do that? Oh, I've called too many things tildes. Oh, sorry. I'm a little inconsistent whether, okay. I used tilde for the second system, which I also had used for the final state of the density matrix. So the density matrix was a path integral on imaginary time beta with systems H at both ends. But the thermophile double state, well, it's a pure state in the combined system H tensor H tilde. So pure state means that only one H should appear only once on the boundary, also H tilde only once on the boundary. The thermophile double state we can represent by a path integral. But now we think of the Hilbert spaces of the two ends as being different. The system and its copy, second copy in the thermophile double. And we take the imaginary time to be beta over 2. And now we can describe in a picture this computation we did in formulas to show that the thermophile double state was a purification of the thermal density matrix. So this picture here represents the ket of the thermophile double state. I'll just repeat it, because here we'll have more room. So the ket we represent by a picture. H tilde is at one end, H is at the other end, and the imaginary time is beta over 2. Except, I'd rather call this the bra, I'm afraid. So then, the ket we calculate by the same picture with the opposite orientation. So H tilde is at the bottom, H is at the top. The imaginary time is again beta over 2. Now how do we calculate the partial trace where we sum over unobserved states of system H tilde? We do that by simply gluing the two pieces of the picture together. So then we just have H at the top and the bottom. The imaginary times add, so the imaginary time is beta. And this picture computes the trace over H tilde of the pure state density matrix. But on the other hand, because we propagated through imaginary time beta, we get a thermal density matrix. Well, I'm cheating with the factors of z. To get the thermophile double state, we really needed this path integral divided by the square root of z, and then the factors of z work out. So now we're going to do this for a conformal field. Any questions on that, those generalities? So now we're going to discuss a conformal field theory. Well, so we'll discuss a theory, a field theory, in 1 + 1 dimensions. So, well, for a while it won't have to be conformally invariant, but after a while we'll assume conformal invariance. So, well, that means that space is simply a copy of the real line. And really, up to a certain point, we could be in any dimension. Then in dimension d, space would be a copy of Rd. To get a thermal density matrix, we do a path integral in a strip of width beta. Where we put our system at the top and the bottom as well. That would compute e to the minus beta h. And then if we want the thermofield double state, well, then we have two different copies of the system, or more exactly, the system and its time reversal conjugate. Okay. The picture tells you that the two should be time reversal conjugates, because to exchange them, you have to flip the time upside down. So time reversal is exchanging h and h tilde. Now with a strip of width beta over 2. And exactly as I explained in this more abstract setup, if we glue this strip to a second strip flipped upside down, also with width beta over 2, we get this picture, which is the path integral demonstration that e to the minus beta h corresponds to the trace over h tilde of the thermofield double state. Now, if you go back to rho beta being equal to so this is what we usually call thermal entropy, which is minus the trace of rho beta log rho beta. But one can view it as the entanglement entropy of the system H in the thermofield double state. So all I'm saying is that, well, in the case of a thermal density matrix, minus the trace of rho log rho is a standard formula for the thermal entropy, but on the other hand, it's the von Neumann or entanglement entropy. Or entanglement entropy in the thermofield double state. So, now, for our infinite volume system, the thermal entropy is trivially infinite. Textbooks will teach you to compute to compute the entropy per unit length. So we could consider a very long piece of this system. And then textbooks teach us that entropy is proportional to the length of the system, with the correction of order 1 that involves how we cut off the system at its boundaries. And when you learn statistical mechanics, what you certainly learn to compute for an infinite system, well, you learned that entropy was extensive, and you computed the entropy per particle for a gas, or the entropy per unit volume for a field theory, and so on. So there's no question but that the thermodynamic entropy of the infinite system is infinite. And likewise, the entanglement entropy between a system and its thermophile double is exactly the same thing, and therefore it's also infinite. So this is an example of a system that, for elementary reasons, has an infinite entanglement entropy in the limit of an infinite system. Now, I actually haven't yet said anything that involves either conformal invariance or 2 dimensions. So this was just a general explanation of what the thermophile double system is and why in infinite volume the thermophile double system has an infinite entropy, infinite entanglement entropy proportional to the volume. However, if we now specialize to a conformal field theory in 2 dimensions, then we can get an interesting new perspective on previous calculation. So in a 1 plus 1 dimensional CFT, so let's say we have space x and imaginary time tau, it's convenient to let z equals x plus I tau. And conformal invariance means invariance to holomorphic mappings. Z to f of z, where f of z is analytic. Well, holomorphic mappings with no branch points. So f of z is analytic, and f prime of z is everywhere non-zero. So when we discuss the thermophile double state, well, this strip has width beta over 2, so we can think of it as the strip where the imaginary part of z is equal to or less than beta over 4. So the thermophile double state is described by a path integral on this strip in the complex plane of width beta over 2, but the imaginary part of z being plus or minus beta over 4 on the boundaries, with h and h tilde on the boundaries. Now we're going to make a convenient holomorphic map of that to something else. What we're going to map it to is a unit disk. Let's say the unit disk where w is equal to or less than 1 in absolute value. And the strip will go to the interior of the disk. The upper boundary h tilde will go to the upper boundary. And the lower boundary h will go to the lower boundary. Now, I'll write a formula in a second for what this holomorphic mapping is. But you might already know that it exists because of a general theorem. The general theorem says that a simply connected and simply connected region in the plane is always holomorphically equivalent to the disk. So here, this infinite strip is a connected and simply connected region of the plane, so it will have a holomorphic map to the disk. But in this particular case, there's an elementary formula, which I hope I have right here. let's, well, I'll partially check it by seeing what that map does to the boundaries. So on the boundary, let's say on the upper boundary, z is I times beta over 4 plus t, where t is real. And that means that w, the beta over 4 times 2 pi over beta, gives us pi over 2. So we get e to the I pi over 2, which is I. So w is I times e to the 2 pi t over beta minus 1 over I times e to the 2 pi t over beta plus 1. So for real t, w always has modulus 1. Because the numerator is minus the complex conjugate of the denominator. As t goes to infinity, the first term dominates and w is 1. As t goes to minus infinity, the second term dominates and w is minus 1. So the only remaining thing to check is whether we go around the circle above or below. So at t equals 0, actually I don't remember, so I'm not sure what answer we're going to get. We get I minus 1 over I plus 1. Okay, so at t equals 1, w is I, so we go around the circle above. So the picture is as I've drawn it. So in a conformal field theory, the path integral in this infinite strip is equivalent to the path integral in a disk. And instead of placing system H on the bottom boundary and system H tilde on the top boundary, we put system H in the bottom half of the circle and system H tilde in the top half. Now, what does this path integral compute? The sort of thing Feynman taught us is that the path integral in a disk computes the vacuum state, or ground state, on the boundary of the disk. Now, if we divide the boundary of the disk into two pieces, H and H tilde, let me call the pieces geometrically A and B. The Hilbert spaces formally are H and H tilde. The density matrix for row A is supposed to be the trace over H tilde of the ground state I'm referring to omega as the vacuum state of our conformal field theory. So the density matrix for system A is simply the ground state density matrix traced over part B. So minus the trace of row A log row A is just the entanglement entropy between A and B in the ground state. So we're going to compute it in a moment, but we computed it in a previous lecture, except that, well, we did something very similar. We took an interval of length L on the line, and we took A to be an interval of length L and B to be the exterior. that was the lecture where we used the replica trick. Unfortunately, that was one of the Zoom lectures, and unfortunately, I think I explained too much in too little time in that lecture. So if you weren't familiar with some of the ingredients, that one was probably hard to follow. And that's one reason we're going to compute the entropy again in a different way in a few minutes. But anyway, we did compute it, and we got an ultraviolet divergence. And now it's obvious why, well, without any computation, it's obvious there must be an ultraviolet divergence. Because in the thermal problem, there was certainly an infrared divergence. In the thermal problem, what textbooks taught you was that you compute the entropy per unit length, not the total entropy. The entropy was proportional to the length. But the conformal mapping tells us that the entanglement entropy between the two sides here is the same as the entanglement entropy between the two sides here. And that's simply the thermal entropy in infinite volume. So without any computation at all, it's obvious that there's going to be an infinite entanglement entropy in this setup. And we can be a little bit more precise about it. Suppose we cut this system off at length L, which we can do by saying that T is plus L over 2 at one end and minus L over 2 at the other end. T was the real part of Z. So at the upper end, well, first of all, okay, I'm putting a cutoff where T is very large but finite. Now, over here, that's going to be an ultraviolet cutoff. The cutoff will, okay, putting an upper bound on T means putting a lower bound on how close we can get to the point W equals 1 or minus 1. And we can make that quantitative because at the upper limit, T is L over 2. So W is I times e to the pi L over beta minus 1 over I times e to the pi L over beta plus 1. That's very close to 1, but to find out how close it is to 1, we write it as 1 minus, or 1 plus I times e to the pi minus pi L over beta. And that's approximately 1 plus 2i times e to the minus pi L over beta. So if L is very, very large, W is very close to 1. But if you want to know how close it is to 1, the UV cutoff on the disk is 2 times e to the minus pi L over beta, where L is the IR cutoff on the real line. So the conformal mapping has turned an IR divergence, which is completely obvious and elementary, and you all knew about it when you learned statistical mechanics the first time, into a UV divergence, which is possibly a little bit less obvious. And the relation between the two cutoffs is this one. Now, that enables us to make a quantitative statement about the divergence of the entropy. So in the picture on the strip, the entropy for large L is a constant little s times the length, where s is the entropy per unit length. Little s is the entropy per unit length, which is the natural thing that you learn to compute when you do statistical mechanics. But we learned that the UV cutoff was 2 e to the minus pi L over beta, which tells us that log 2 over epsilon, well, log 1 over epsilon minus log 2, I guess, is pi L over beta. So L is beta over pi times log of 1 over epsilon plus a constant. So the entropy is going to be something times beta over pi times the logarithm of 1 over epsilon. So the conformal mapping between the strip and the disk tells us that in 1 plus 1 dimensions, there's going to be a logarithmic divergence in the entanglement entropy between two regions. Now you might remember that in the Zoom lecture I explained this in a different way. What I said in the Zoom lecture was the following. We considered in the plane an interval of length L, and we said that on dimensional grounds, the entropy, since it's dimensionless, is only a function of L over epsilon, where L is the length. Yeah, okay. It's okay, I think, to call this L. They're both one-dimensional lengths, although a different setup. Here, in this setup, L is going to infinity. In the other setup, L was a finite length, and we were computing the entanglement entropy as a function of L. On dimensional grounds, it was a function of the ratio L over epsilon. But I also said that epsilon d by the epsilon of S is independent of L. That was because the dependence on epsilon can only come from an ultraviolet divergence. And an ultraviolet divergence will be local and doesn't know how far away the other boundary is. So combining the two facts, we learned that the entropy had to be a constant times log L minus log epsilon. That's the most general function of L over epsilon that satisfies the fact that the epsilon dependence is independent of L. And then we computed with the replica trick, and we found the coefficient of the logarithm. So in today's discussion, again without any computation, just on very general grounds, we've discovered that the entropy has to have a logarithmic divergence. And we have a new interpretation. The coefficient of the logarithmic divergence is the thermal entropy per unit volume, little s, times beta over pi. Yes?
I think there may be a sign problem because log 1, I think it should be log 2.
Where should the log 2 be? Here?
Yeah, there. And I think on the left side that's plus.
Okay, that could be. But it's a little bit non-universal because I didn't tell you exactly, I didn't tell you exactly how to do the cutoff. So different cutoffs, I said that the entropy was S times L, but it's really S times L plus a constant of order 1 that's non-universal and depends on the cutoff. And I imagine you're correct in correcting me, but we're ultimately are going to only care about the logarithmic term, which is universal. Any other questions or comments? So, to complete the story, we should calculate the entropy per unit volume of the thermal problem. I do hope I have the beta over pi correct here, because otherwise it will spoil the punchline in a little bit. Yes?
I guess here you meant to say L is beta over pi log 1 by epsilon, right?
No doubt, yes. Thank you.
That's
Okay. Yeah, sorry. We don't, as I just said, we don't care about the log 2, but we do care about the log 1 over epsilon. Okay. I hope that didn't cause too much confusion over here. But okay. Thank you. So we want to compute little s. For a conformal field theory in 1 plus 1 dimensions. So a general relationship between the partition function and the entropy in statistical mechanics is what I've just written. I imagine it was part of of learning statistical mechanics. Now here, how would we compute z? Well, z is trace e to the minus beta h. So to compute a trace, we do a path integral in a circle of circumference beta. But now we also have one dimension of space. So this distance will be L, and the circumference of the circle is beta. So we have to do that path integral. The way to do that path integral is to look at it sideways. In the explanation so far, we have a quantum state on this interval of length L that propagates through imaginary time beta. But we can look at the same path integral backwards and say that a quantum state on the circle, where the circle has circumference beta, propagates through imaginary time L. We're interested, so in that interpretation, so there's an initial and final state at the two ends of the cylinder, and the path integral is a matrix element between the final state and the initial state of the exponential of minus L times the Hamiltonian on a circle. I'll call H beta is the Hamiltonian on a circle of circumference beta. Now, we could write this as a sum over eigenstates of the Hamiltonian. But we're interested in the limit of very large L. And for large L, so I haven't told you what the initial and final states are. That depends on how you cut off the problem at large L. So whatever cutoff you used at large L gave some initial and final states in the path integral in the circle. And we'll see in a moment that that will only affect the large L answer by a constant independent of L. For large L, the ground state dominates. And now we're going to need to use the same fact about the Casimir energy that we used in the other computation of the entropy. The Casimir energy, or ground state energy, of H beta is minus C over 12 if beta is 2 pi, and otherwise it's minus C over 12 times 2 pi over beta. So then Z for L large, well, we approximate it by just the ground state contribution, propagating the ground state through an imaginary time L gives a factor of e to the L times C over 6 pi over beta. And then we have the matrix element of the ground state to the initial state. So whatever the initial and final states are, we assume they have some non-zero overlap with the ground state. And whatever that is only affects Z by a multiplicative constant independent of L. So log Z is then L times C over 6 times pi over beta plus a constant that depends on cutoff. The constant is an edge effect at the boundaries. So If you take a thermal system, but you cut it off at finite volume, you might use Dirichlet boundary conditions, Neumann boundary conditions, something else. So the entropy will receive a contribution of order 1 depending on the boundary condition, and that shows up here in this matrix element. But up to a constant, and then there are terms of order e to the minus L. There are contributions of states of higher energy, and those contributions decay as powers of e to the minus L. So, we can plug this into the formula for log z. So the entropy is 1 minus beta d by d beta of log z, which is L times c over 6 times 2 pi over beta. Oh, sorry, pi over beta. So that's equal to L times c over 3 times pi over beta. So now if we just remember our formula for the ultraviolet cutoff, the UV cutoff was 2 times E. Well, maybe I should just use this formula. The relation between L and the UV cutoff was that L was beta over pi times the logarithm of 1 over epsilon plus a constant. All these formulas have constants in them. So now the beta over pi cancels the pi over beta, and we get c over 3 log 1 over epsilon. So we've again computed the ultraviolet divergent part of the entanglement entropy in 1 plus 1 dimensions for a conformal field theory. However, because it's an ultraviolet effect, conformal invariance is not very important. If you have a non-conformal field theory, which is conformally invariant in the UV, it would have precisely the same ultraviolet divergence in the entropy if you have a non-conformally invariant theory, you can't conformally map the strip to the disk. But you can do the computation of the entropy on the disk. And at short distances, it will have the same divergence as if the conformal field theory was not perturbed by relevant operators. So this is more or less a universal computation of the divergence of entanglement entropy in 2 dimensions, even though we did the computation for conformally invariant theories, because more or less any theory is conformally invariant at short distances, or very simply related to a conformally invariant theory at short distances. There's really only one more thing I want to say about this. So, let me see. I want to give a little bit of intuition about it. So, in the thermal picture, let's go back to the thermofield double state. So we have a system A with Hilbert space H at the bottom, a system B with Hilbert space H tilde at the top. If you consider a mode which lives here, it's entangled with some mode of the other system, but it's mostly entangled with modes that are physically nearby. So this mode is mostly entangled with one which is here. This mode is mostly entangled with one which is here. And if you have a mode which is very far to the right, at the bottom, is mostly entangled with a mode that's very far to the right at the top. Now, what I'm saying, okay. So if we go to this picture, that tells us that the more we get to a mode which is close to the boundary on one side, the closer are the modes on the other side that it's mostly entangled with. So you can think of the infinite entanglement entropy as meaning that a mode at distance epsilon from the boundary is entangled with a mode the same distance on the other side. A mode epsilon over 2 away is entangled with one that's epsilon over 2 away. A mode that's epsilon over 4 away is entangled with one that's epsilon 4 away, and so on. So the closer and closer you get to the boundary on one side, the closer are the modes on the other side that it's most entangled with. If we take a mode of some fixed wavelength in this picture, it maps on the other side to one that's, assuming that it's very far to the right, where we're probing the infrared divergence, it'll map to one which is very close to the boundary and also very high wavelength. So the picture is that the entanglement entropy diverges because of very short wavelength modes very close to the boundary on one side being entangled with very short wavelength modes close to the boundary on the other side. Okay, so that's it for today, and what we're going to do next Tuesday is to make concrete the idea that there's no Hilbert space decomposition and explain the assertion that an observer on one side has an algebra, not a Hilbert space. And after doing that, we'll then discuss, possibly we'll start that Tuesday, what you have instead of density matrices in quantum field theory, or to what extent you can imitate some of the, well, the main goal will be to explain that you can define relative entropy in quantum field theory and understand its properties. So anyway, we're finished for today, but are there any questions before we say goodbye?
If we don't purify the state in thermal field double,
Yes?
do we still have space-time feature like for other purifications?
Well, the question is, the thermal field double has a very nice path integral representation. I think the question is, do other purifications have a path integral representations? Well, some will. Well, see, any two purifications on the same Hilbert space differ by a unitary transformation on that Hilbert space. So if you want the second Hilbert space to be a copy of the first one, all you can do is to apply a unitary transformation on the second side. So your question would then, be, in that example, would be equivalent to asking, for what unitary transformations do you have a reasonable realization by path integrals? To some extent, that depends on what you consider reasonable. Some of them would have simple descriptions, some not. Any other questions? Okay, then we'll call it a day. See you on Tuesday.